Hi, this is Miss Oliva, and I'm going to go over logarithmic functions. Logarithms are the inverses of exponential functions. So it's going to be similar to what we did last time, just again with x's and y's switched. So definitely make sure you've done 3.2 before looking at 3.3. Okay, so this is what we were going over last time. Things in exponential form, where there was a number raised to a power equaling our value. But now we're going to be doing the opposite. So these are inverses. So the first thing you need to know is that a log, even though it's weird to see this whole word in the middle of a problem, it just is talking about the exponent. So when you see log base b of x, it really means b to what power is x. So the first skill is getting used to going back and forth between these two models. Okay, so 3 to the negative 2 is 1 over 9. Hopefully, we're all comfortable that that is true because the negative 2 takes it to the bottom and then you have to square it. So hopefully you're comfortable with this. So now where would these numbers go if I wanted to rewrite this in its log form? So log, so you can use the example up here. The base, where the 3 is, becomes the little number here. The 1/9 goes next, and it's that exponent that goes all by itself on the other side, right? Because log means 3 to this power over here equals this. So it's just getting used to what number goes where. So here, log, the base is 10 of 1,000 equals 3, but 10 is the standard log. So it's not wrong if you write it, but you do not need to write it. So this would be the same thing. So from now on, when you don't see a number there, you know it's 10. Last one, we have fractions, but that doesn't matter. We still put them where they're supposed to go. You can use parentheses if you want, but it should be like that. So now going the opposite way is usually easier because it makes a little more sense to us. This, it's not obvious if I did this right or not, so I need to be really careful that I put things in the right spot. But here, if I know to start with this number and always raise it to the answer, then the only thing left is the 27, and I can easily check if that makes sense. Is 3 to the third 27? Because otherwise I might have made a mistake. So next one, 2 to the negative third equals 1/8, and that is true. So again, hopefully you're getting more comfortable that these negatives don't mean negative. They mean it's going to become a fraction. And then finally, this one again has no number there, but I know what that means. It means there's really a 10. So 10 to the second power equals 100, which is true. So it definitely takes some practice going back and forth. So I would do this a few times until you get the hang of it and can do it without looking back at the examples. So now there's a special log called ln, which is called the natural log. And all it means is the base happens to be an e. So they just gave it a special name so there wouldn't be so many letters here. So ln means log base e. So if I had something like ln1 equaling 0 and I wanted to rewrite that, it would be e to the 0 equals 1. And we know that's true because anything to the 0 equals 1. And so if I was trying to go the other way, I would probably at first say, okay, I'm used to doing log to this of that. And then I'd notice, oh, this is weird. We don't ever really write log base e. Instead, I'm going to write ln 1 equals 0. So going back and forth the exact same way, just if you ever notice that you're about to write a log base e, just know that that is when we use the ln instead. But going back and forth is the same. And since this means this, This is a property we're going to need to start getting comfortable with, that if we ever do see ln1 in the problem, we're going to hopefully start realizing that that just equals 0. So you should never really have ln1 in your final answer. You should be able to replace it with a 0 and move on. Okay. So if they ask me to do some of these without a calculator, what I'm thinking in my head is 5 to what power would get me 25? And you can write it out if you prefer to see it. But for some of these, you shouldn't need to, right? 5 to what power is 25? 2. So I made up that x. It wasn't really in the problem. So really, log base 5 of 25 apparently equals 2. That's it. That whole thing just equals the nice number 2. So obviously, we're going to want to replace these with what they equal if it's something nice. So how about this one? Remember, this really means 10. So 10 to what power would get me to here? Well, with tens, it's nice because however many zeros are is what you'd need, right? 10 to the second is 100, which is 2 zeros. 10 to the third is 1,000, which is 3 zeros. So 10 to the fourth is 10,000. This one's a little trickier because of the fraction, but I'm going to first think, how would I get from 3 to 81? And then I'm going to know that because it's a fraction, that just means I need to add the negative sign. So 3 to the fourth power is 81. So that means 3 to the negative fourth power would take that 81 to the bottom. So if you haven't done a lot with negative exponents, you might want to write yourself an extra little note here to remember that if you're going from a normal number to a fraction, there has to be a negative involved. All right, now there's some little tricks that we need to know that make a lot of these problems easier. I want to make sure you're aware of them. The first is that if you have the same base, because remember, ln is really log base e, if you have the same base as the number here, these just wipe each other out and you're just left with that extra number. So whenever you see ln and e next to each other, they go away. So we almost have this here, but that e's in the bottom. So I'm first going to just rewrite this because 1 over e to the 8th is the same as e to the negative 8. And now they're right next to each other. So I can wipe them out and know that I have that negative 8 left by itself. Okay, this is similar to b, except you might not be as comfortable with the decimals. So you can always kind of guess and check in your calculator. So 10 to what power gives me this? Well, I know it's going to be a negative because the positives give me larger numbers like 10,000. So in this case, you got to be a little careful because it's not just a matter of counting the zeros, because that decimal also needs to go in front of the 1. So if you guess and check, you'll end up seeing that it's -7. But now I see a base the same as the number with it. So just like ln e, log base 9 of 9 wipes out and you're left with just that 12. And that also works if it's written the opposite way. If it's a base raised to the log of the same base, those also wipe out. So you're going to start getting used to seeing some of this stuff and getting happy and knowing, okay, this part's easy. So last one, 7 raised to log base 7 of 18 just gives us 18. Okay, so here are just some little tricks that help make these problems easier once we get into the more complicated problems with solving with logs. So you're going to need to be comfortable with these first. Okay, let's talk about negatives and zeros. Can we ever have a negative here? Well, remember what this means. This means that 3 is being raised to some power to get to -2. And that cannot happen because even if the x is negative, remember that's just going to give you a fraction. So there is no exponent that I could ever raise 3 to become a negative anything. So that means that this number cannot be negative. How about 0? Well, this would mean that 3 raised to the x equals 0. And again, that cannot happen. We know that 3 to the 0 is 1, but 3 to the 1 is not 0. If I put negatives in here, I get a fraction. So I can play around with this for a while, but there is no way I'm going to find an exponent here to get to 0. So this can't happen either. So that means whatever we're taking the log of, so whatever goes here, needs to be greater than 0. It cannot be negative, and it also cannot be 0. So that's going to be important when we start doing domains. Okay, but before we do domains, we're going to talk about the graph. So remember I said that logs were the inverses of exponential functions. So that means that all of the x's and y's are switched, which also means that the graphs are the graphs you would get when you flip the graph over y equals x. So the easier way to think of this is to kind of convert it first. So this is the same as saying 2 to the y equals x. So when I go to make my chart, I'm actually going to start by picking y values, which we never usually do, because that's going to be easier to find the x. So if I plugged a 0 in for the y, 2 to the 0 is 1. If I plugged in 1 for the y, I would get 2. If I plugged in 2, I'd get 4. Now let's go the other way. If I plugged in a -1 for y, 2 to the -1, remember, just means 1 over 2. And if I did a -2, it'd be 1 over 4. But again, no negatives, right? But do you see that this is the opposite of the type of thing we were getting when we did exponential functions? We would have 0, 1. Now we're getting 1, 0. We were plugging in 1 and getting 2 for something like this. Now it's the opposite. So if we plot some of these points, we'll see what happens. At 1/2, we get -1. At 1/4, we get -2. So do you see how, again, we're getting closer and closer to something, but it's the y, it's the y-intercept or the y-axis instead of the x-axis, which means our vertical asymptote this time is going to be x equals 0, which again makes sense because we said that the x's and the y's are going to flip. So if for exponential functions, we were always having y equals 0 as our exponent, it makes sense that now it's x equals 0. And our graph is hugging the asymptote down here, and then it's just going to slowly get bigger and bigger and bigger and bigger. So our domain is not all real numbers because we're never over here. The x values this time are never getting negative. So our domain is 0 to infinity because we're starting at that asymptote, but never quite hitting it and going to the right forever. And this time our range is coming from -infinity and going to positive. So again, if you were to look at what we did last time, these are flipped. It was the domain that was always all real numbers and the range that wasn't. So let's try another one. So again, I'm going to start with my y values instead of my x. And I'm going to maybe even rewrite it to make it easier for me to think of instead of dealing with these logs. So if I plugged in 0 for my y, I'd get 1. If I plugged in 1, I'd get 3. If I plugged in 2, I'd get 9. Now let me do some negatives. If I plugged in -1 for the y, I'd get 3 to the -1, which is 1/3. And plugging in 2 gets me 1 over 9. Plugging in -2. So plotting these again. 1, 0 is here. So do you see how, again, they're sharing that one nice point, just like our exponentials were sharing it here. It's just the opposite. Instead of 0, 1, it's 1, 0. And 3, 1, 9, 2, somewhere way out here. Let's go the other way. A third, -1, and a ninth, -2. Again, hugging this asymptote. So domain is again starting at 0, but not hitting it and going forever. Range coming from the bottom going to the top. We use all real numbers. And that asymptote is vertical this time. So x equals 0, not y equals 0 like we had when we did the exponentials. So just like a lot of what we've been doing, if I were to talk about transformations, this +4 in here really means go to the left 4, and this +5 out here by itself means up 5. So you shouldn't have any problem in the homework using the graph to just move stuff around. So this is considered inside the function, so it's the opposite, and it's left or right. Anything out here is up or down, the same that you would guess. Plus means up, minus would mean down. Okay, now for domain. So with log functions, remember you can only take the log of a positive number, which means whatever's in here needs to be positive, which means it needs to be greater than 0. So when they're asking me for the domain of this, I take whatever's inside, set it greater than 0, and solve. So I'm going to add the x to the other side. So remember, be careful when you read this. It's not greater than because I'm going to start here. So it's really x is less than 7. So interval notation would look like that. All of the x's need to be less than 7. Because if it was 7, that would give us 0. And if it was anything bigger than 7, it would give us a negative. So number 2, same thing. Start by setting whatever we're taking the log of, make it greater than 0, and then solve. So now I need to be greater than 3/2. So parenthesis, because we don't want to be equal to 3/2, and going to infinity. Okay, we're going to look at the homework to see the 1 or 2 word problems. If I have it open. Might need to find it real fast. Okay, I have found it. So this is number 18 on 3.3. It's talking about the intensities of earthquakes and that they're measured with seismographs all over the world at different distances from the epicenter. Suppose the intensity of a medium earthquake is originally reported as 10 to the 5.6 times I sub 0. So I sub 0 is just the original intensity. Later, the value is revised as 10 to the 5.8 times I sub 0. The local magnitude M on the Richter scale is given by this formula that you take the log of I divided by I sub 0. So there's a lot going on here. They want us to determine the magnitude of the earthquake using the original estimate for intensity. So let me show you what all that means. Because this is not hard, but it's just a little hard to understand what they're asking for. So for 18, they've given us this formula to find the magnitude. And they want us to use the original intensity that they said they found, which was 10 to the 5.4 times I sub 0. So basically, they're just telling us to plug this in to the formula. So the magnitude would equal log of our intensity, which they said was that, divided by I sub 0, according to the formula. And we can reduce this by crossing out those I sub 0s. And we get this, but log with nothing here really means there's a 10, right? So in this a log base 10 of 10, which is the nice thing that happens. So that wipes out, and our final answer is just 5.4. So next, they want us to do the same thing, but with that second intensity they mentioned. So again, we're going to go to that formula, plug this in for the top part, divided by I sub 0, which is nice because we don't know what that is, but they cross out, so it doesn't matter. And that leaves us with log 10 to the 6, but log and 10 wipe each other out, and it's just 6. So it was really just a matter of being able to follow that they were giving you a formula and they were telling you what you could plug in there. If you did that, it would end up working out nicely. Final question it's going to ask is how many times more intense was that second one than the first one? And if you're ever asking how many times more something is than something else, you always just divide. So we would take our bigger intensity, and to see how many times bigger it was than the other one, we just divide by the other one. Again, it's weird that both of them had this weird times I sub 0 when we don't even know what that is. But because they both had it, again, it doesn't matter what it is. So all we really need to do is 10 to the 6 divided by 10 to the 5.4. And they asked us to round to 1 decimal. And I got 3.98, etc. So be careful with your rounding. If we're rounding to 1 decimal, that's right here, but there's an 8 next to the 9. So the 9 is going to go up to 10, which really means that we have to add to the 3 as well. So 3.98 really rounded all the way up to 4.0 or just 4. So even though it said round to the 1 decimal place, your final answer is just 4. So make sure you're okay with rounding, or that's going to mess you up on some of these. Okay, going back to the homework, because the next one has a lot of writing as well. So I just wanted to point out what it's asking. So 19 has a lot going on here. It's basically just giving us a range of these pH values. And then at the end, it's just asking us to find the pH value for the cola and for the wine. And so all you really need to do is plug each one into this formula. So it's similar to the last one where there's a lot of writing, but not as much going on. So I'll show you kind of how to get started. Okay, so looking at number 19, which we just looked at, I think this was one. Okay, they gave us a formula to find the pH of each thing. So we're talking about, I believe, cola and wine in this example. And the H plus that you need to plug in here, they gave you also. So if I'm trying to find the pH value for cola, all I needed to do was plug in what they had given us as the value for cola. You could make this a little bit nicer because 3.1 times 10 to the negative 3, if you remember scientific notation, just means to move that decimal 3 places to the left. So you don't need to do this, but I prefer to write it this way because that's easier to put in the calculator. So make sure you're okay that these mean the same thing because I just moved the decimal 3 to the left. Putting this in the calculator, I believe gives you 2.5. I'll try it again, just to double check. Okay. So I think in your homework, it asks you to write it this way and then give your final answer. So doing wine would be the same thing. Same formula. I'm just going to plug in the other H plus value. Again, you can leave it in this form, but I'm going to go ahead and just move my decimal 4 to the left. So this time it's in front of the number. So that's going to make me add 4 zeros in front of 7. But if I plug that in, I get 4.2 if you round to the nearest tenth like they asked. So somewhere in that long explanation, in case you didn't catch it, they explained that the pH ranges from 0 to 14, and that right in the middle is where they put water. So anything less than 7 ends up being acidic, and anything greater than 7 is alkaline. So basically, the smaller your pH value, the more acidic. So I believe the last question they're going to ask you, which of these is more acidic? And it would be cola because it has the smaller pH value. So the smaller the number you get, the more acidic it would be. And that's it for that section, 3.3.